Hi, I'm Alistair and I'm an escape room designer. So I create electronic puzzles that players interact with in lots of different ways, using sensors and buttons and sliders and knobs. But the problem with these inputs is that they're often not particularly robust, especially given the rough handling they normally get from escape room players. And you also find this with things like interactive museum displays, or in fact any piece of electronic hardware that's used by the public. And there's nothing more frustrating for them than coming across a piece of broken tech. So how do you make these inputs more robust? Well, you could use something like this, which is designed for controlling industrial machinery. But these kind of inputs are normally quite bland and boring. Or you could use a button that's designed for an arcade machine, but well, these are normally a bit garish. So in this video, I'm going to show you an alternative way to create your own customised heavy-duty analog inputs that you can use in any electronics project using plumbing levers like these. So here I've got two regular plumbing valves. I've got a lever valve and I've got a rotary gate valve. And these are the sort of things you'd use to isolate the water supply in your home. If I show you a view down the end, hopefully you can see. So at the moment the valve is open and you can see my hand all the way through the pipe. And then as I close the valve, what happens is that a shutter closes in the middle here, and that would stop water flowing through the pipe. And these two work in the same way. The main difference is that the lever valve only takes a quarter turn to go from fully open to fully closed, whereas the rotary gate valve, you have to rotate the wheel quite a few times here to do the same thing, to make the shutter fully come across the pipe. So how could we turn these into an input that you could detect using an Arduino or a Raspberry Pi? Well, if there was water flowing through these pipes, we could put a water flow sensor in the pipe here. But mixing liquids and electronics is not a great idea if you can prevent it. So instead of having water flowing through the pipe, imagine instead that we have light flowing through the pipe. So here I've got an LED. I'm just going to insert that into the pipe on one side of the valve here. And now if I show you again the view down the end, so this is with the valve fully open, you can obviously see the light from the LED coming out the end. And as I close the valve off, hopefully you'll be able to see gradually the intensity of the light going down to the point where the valve is fully closed. You can't see any light from the LED at all. And then as I open it up, you'll be able to see that intensity grows and grows until the maximum there. Now, if we were to have a light dependent resistor, let's say, inserted into this section of the pipe here, we could then use that to measure how far the valve had been opened. When the valve is fully closed, this section of the pipe here will be completely dark, assuming it's sealed off at this end. That means that the resistance of the LDR will be very, very high. As the valve opens and more light falls on the surface of the LDR, its resistance drops. And we'll be able to measure that resistance using a voltage divider circuit and any analog pin on an Arduino. And here's an illustration of a circuit you could use to do that. So over here I've got my LED on one side of the valve, and that's connected to a 5-volt DC power supply through a 220 ohm current limiting resistor. Notice that this actually isn't connected to the Arduino at all. This is just its own freestanding circuit that will keep the light constantly lit. Then we've got our valve, and on this side we've got our light dependent resistor, which is connected in series to a 10 kilo ohm fixed resistor. And those form a circuit that goes from the 5-volt out from the Arduino, first through the light dependent resistor, whose resistance is going to vary depending on the amount that the gate is open, then through the fixed resistor, and then finally back to ground. And we have a line that's going to one of the analog input pins, A0, and that's going to take a reading at the midpoint between the variable and the fixed resistor. So this is called a voltage divider or a potential divider circuit. And when you have multiple resistors in series like this, the way that voltage is dropped across the circuit is in the same ratio of the resistor's value to the total resistance of the circuit. So let's say that the amount of light falling on the light dependent resistor was enough to cause it to be 10 kilo ohms of resistance. So we've got the same value, we've got 10 kilo ohms here, we've got 10 kilo ohms here. So we would expect the 5 volt here to lose half of its voltage across the first resistor and the other half across the second resistor, so that by the time it got back to ground again it was at 0 volts. So if we were to take our analog reading here at the midpoint here, we would expect it to be exactly 2.5 volts. Now let's say that we close the valve slightly, which means that the light dependent resistor's value increases to 20 kilo ohms. Well, at that point we've got 2/3 of the resistance of the total circuit is at the LDR and only 1/3 is the 10 kilo ohm resistor here. So we'd then expect 2/3 of the voltage to be dropped at this midpoint here and only 1/3 afterwards. And that would give us a reading of 1.6 volts at the analog input pin. So the more the valve is closed, the less light falls on the LDR, its resistance goes up, and that means that more voltage is lost in the first part of the circuit and the reading on the analog input pin goes down. And here's a simple sketch you could use to measure that input. So I'm simply taking an analog read from the input pin that's connected in the middle of my voltage divider circuit, and as well as taking the current reading recorded there, I'm also going to keep track of the minimum and the maximum values that have ever been read at that analog pin there. I'm just going to plot those using the Arduino serial monitor graph. So I'm going to plot first my minimum reading, then my maximum, and then the current value in a comma separated list. I'm going to out that to the serial monitor and then just delay by 10 milliseconds each frame. And if I load the Arduino serial plotter, you'll be able to see those values illustrated on this graph. So as I move the handle, you'll see that the green line there, that shows the current value being measured by the sensor. The blue line at the bottom is the minimum value that's been recorded, and this red line at the top is the maximum value. As I open the valve more and more, you'll see that that pushes that maximum line up. So when I've opened and closed the valve fully a few times, you'll see that the range of values I've recorded goes from a minimum of about 150 to a maximum of about 850, with a midpoint of around 500. And that's exactly what you'd expect from the 10-bit analog to digital converter on the Arduino, which maps voltages from 0 to 5 volts into the range of 0 to 1023. Now, you could either use this as an analog input by taking the raw reading of the sensor as shown in the green line there, or you could remap the scale of values based on the minimum and maximum values recorded, or you could use this as a digital input by just setting a threshold value of the midpoint, which is around 500, and measuring whether the current reading was above or below that midpoint to decide whether the valve was open or closed. So you can use this input in different ways, and because the lever is all metal, it makes it sturdy and satisfying to operate. But one thing I should mention is that when you insert electronic components and wires into these copper pipes, you need to make sure they're properly insulated in rubber shrink tubing so that they don't touch the metal and cause a short circuit. In the next video on this channel, I'll show you an example of how you can use inputs like these in an escape room puzzle.